Hello, hello.
Is it working? Yeah, good.
Thank you, Kuntal, and good morning and good afternoon, everyone. So this talk is on Indian planetary. Can I have the lights off on this screen? Yeah. So as Dr. Shankar was mentioning that PRL is the mother of ISRO, because all research activities started in PRL under the leadership of Dr. Sarabhai, and that's why he is called as the father of Indian space program. So when I talk about the planetary exploration, it's not loud. Can you just increase the volume slightly? Is it better now? Okay? No? Okay, so I hope it is better now. Yeah, okay, perfect. So I'm going to give you glimpses of what's happening in terms of the exploration program within the country for looking at the planets or the solar system bodies, starting with the Chandrayaan-1 mission, moving on to Mangalyaan, then Chandrayaan-2, now Chandrayaan-3, and what is stored for the future. So as you see over here down, I think still a lot of lights are coming up on the screen. So we are seeing the glimpses of various missions starting from the Chandrayaan-1 over here. We have the Mangalyaan, Chandrayaan-2, and most recent one, of course, the Chandrayaan-3 mission. So starting with the exploration program, I should mention about Dr. Sarabhai, who actually started the whole space research activity in India by establishing the Physical Research Laboratory in the year 1947. And all the space science activity, whether we talk about the rocket launching programs, the balloonings, the satellite, they all started under his leadership. And here you are seeing Dr. Sarabhai along with Dr. Kalam over here, and Dr. Madhavan Nair, who was later on the chief of ISRO. When you talk about the rocketry program, which is essential to explore the space, it started in 1963 on 21st of November from Thumba coast, and this carried experiments which are developed in PRL. Now moving on to how does we start the exploration program as a history and legacy in the country. As I just mentioned over here, it all started in 40s by establishment of PRL. We started with sounding rockets. We had formidable years of balloonings also. And then came the Aryabhatta, the first satellite which was launched by India. Subsequently, we had various other space missions. I'm not talking about any other remote sensing and communication satellite over here. But we had the first mission as Chandrayaan-1 in 2008. Subsequent to that, Mars orbiter mission in 2013. Chandrayaan-2 in 2019, and then subsequently the Chandrayaan-3 the last year. And this journey is going on with Aditya now working at L1 point. So starting with the Chandrayaan-1 mission, which we had in 2008 October, after 16 days of travel, we reached the moon carrying 11 experiments on board, and 3 were being flown for the first time. This was truly international character with 10 countries participation. You can see the whole spacecraft completely loaded. You can see it much better over here. We also had a MIP, Moon Impact Probe, which also carried an experiment called CHASE to look at the abundances in the atmosphere or exosphere of the moon. And this MIP was actually released after we reached the 100-kilometer circumpolar orbit. And it became the first man-made object from India to actually land onto the lunar surface. And it landed at 70 degrees south, providing us a lot of information during its course of landing from 100 kilometers towards the poles. So this is what the trajectory of this MIP, Moon Impact Probe, which is sitting on the Chandrayaan orbiter. And it started somewhere very close to the equator and landed at 90 degrees south. It also provided us information about the distribution of argon and H2. One can use this because these are basically no collisions happening, so you can scale height can be used to convert this kind of information into a map of altitude versus latitude. Or you can also look at the distribution of neon, which was done for the first time, where we see how the distribution of neon actually changes in the exosphere of the moon. We also have discovery of water. I don't know why this figure is not coming out well. There's a lot of change which is happening with respect to what is seen here on the screen. Is a color issue somewhere? No, even this is not the color. The color is very different. maybe there is an issue with respect to the conversion of the slides on the displays. But this gives you distribution of water, because Chandrayaan mission actually discovered water on the moon, and we also found that there is more water in the polar regions. This is possible because of the bend absorption feature, which you see very close to 3 micron, which is possible only because of OH or H2O molecules present on the lunar surface. In addition to this, of course, we knew a lot more about many other things, and I will talk a little bit about the SAR experiment where I was directly involved using CINA and SWIM, the 2 sensors which is sitting on the top deck. So as we know that as the moon goes around the Earth, it passes through different environment. In this part of the orbit, it is in the pure solar wind, but as soon as it enters the magneto sheet or magneto tail, it is looking at the plasma, which is very different than the pure solar wind. Now, there was an instrument called SARA, which was looking at the plasma which is coming and hitting the lunar surface, as well as looking at the formation of energetic neutral atom from the lunar surface by this interaction. What we were knowing so far was that the solar wind, which is a plasma coming from the sun at a speed of 400 km per second, comes and hits, gets completely absorbed, and there is a long wake which gets filled up due to anacoustic speeds at several lunar radii downstreams. We are also knowing that there are some magnetic anomalies on the lunar surface. This simple picture has completely got changed by this experiment, and now we know, oh boy, there's a lot of issue, I think, with respect to the slides, where we now know that a significant amount of the impacting solar wind protons get converted in neutral hydrogens and comes out from the lunar surface. We also see sputtering of oxygen because moon is full of oxides. There's almost like more than 50% oxygen in form of oxides. And we also discovered mini magnetosphere on the lunar surface. If you look at this, you can look at this picture where we actually gave the impacting solar wind changes with respect to ENAs. ENAs means energy neutral atom, which is produced by the impacting solar wind protons, having a charge exchange at the surface and releasing out energetic hydrogen. There's enough energy loss of more about 50%, but backscattering fraction is about 20. And therefore, there was a ESA press release which talks about hydrogen offers a new way to study the moon. We also looked at the magnetic anomalies and found that the regions where we have magnetic anomalies of about few tens to few hundreds of nanoteslas, the solar wind is not able to impact that region, and therefore you don't see any production from this, and it looks to be dark, and that's why it came as a cover page of GRL. We also looked at the ions present in the plasma environment around the moon, and we found that we could very clearly see the impacting solar wind, which is seen over here, doubly ionized hydrogen or alpha particles, helium or alpha particles, but energetic ions which have energies much higher than the solar wind itself, which are basically pickup ions. And we also see ions in the night side. And that was a clear indication that there is a plasma present at 100 km circular polar orbit in the night side of the moon. Subsequent to that, we found out what could be the possible processes by which the ions are reaching the night side of the moon, but they are actually impacting, and which came from the signals of observations of hydrogen ENAs. That means the solar wind is not just reaching at 100 km, but it is actually impacting the night side of the moon. Talking about ions, we also used Indian Deep Space Network at Bailalu, very close to Bangalore, to use the MESSER sitting over here to log the Chandrayaan-1 oscillator, spacecraft communication system oscillator, so that we can get a stability of about 10 to the minus 15 and use that to infer the electron densities through radio occultation experiment, and found the densities of about few hundred particles per cc. Of course, this was not planned, but it was done, and we got a very exciting results from this. In addition to this, the Chandrayaan-1 mission talked about volcanic and tectonic activities. That moon is not geologically dead, it is very active, and recent past activities in 50 to 100 to few hundred millennium or geological time scales of this has been there, and this is not just from few observations, multiple observations are now telling that volcanic activity has happened in the very recent past, or you talk about recent volcanoes inside the Kruger craters, or even talking about volcanic activities at Lowell crater, which talks about 2 to 10 million years. In addition to this, if you look at what Chandrayaan-1 did to our understanding, so it discovered water on the moon. It is there on the surface, below the surface, above the surface. It is more there in the polar regions, of course. Moon is dynamically, tectonically, and volcanically active. We have impacting solar wind getting converted into ENAs, and more than 20% of it is actually coming out. And then a lot of populations around the moon, particularly in the night side, where we are all thinking that plasma is devoid. And then, of course, a lot of places where human habitat can happen in the future. More than 240 scientific publications has come out from this mission. Mars orbiter mission, well celebrated mission, because launching on 5th of November of 2013, after 10 months of journey, we reached in September 2014, and India became the first country in the world to have the successful insertion of an orbiter around the Mars in the first attempt. This was having a lifetime of 6 months, but it actually worked for more than 8 years. There were 5 experiments on board, and I was directly involved with the Menka experiment over here, which was looking at the exospheric neutrals present in the Martian atmosphere. They are all situated at different places of the spacecraft, depending upon the science, what they're planning to do. We got a lot of information about the seasonal variabilities which is seen on the Mars. Mars also has season like the Earth. And if you see this compared to this, you will see that seasonal variability is very dramatic because the Martian orbit is much more elliptical compared to that of the Earth. We can use MCC, this is RGB. So in the red, we can actually see the superficial features. In the blue, we can see the clouds and dust which is present. This is the polar cap image made from a mosaic of various observations, clearly showing how the ice in the polar cap regions of the Mars changes as a function of season. Or the Phobos, which is a small satellite of Mars, or the Deimos, the 2 very small satellites seen very clearly because of the highly elliptical orbit of the MOM mission around the Mars. Dust clouds are a regular feature in the case of Mars, and this is a picture of Valles of Marineris, one of the biggest canyon in the solar system, completely filled with clouds and dust, but in another season, you can very clearly see this. Or in addition to this, you can actually see very clear signature of flow channels in the case of Mars. This is the case of Mangla Valley, where you can very clearly see the channels being produced because of flow activity happening in the past in the Mars. So Mars has been believed to be hot and wet in the past. Currently, it is all cold and dry. We also see clear signatures of orographically controlled clouds. This is the image of Olympus Mount, which is the highest mountain in the solar system. It is 3 times higher than the Mount Everest. And this is a phenomena which basically a formation of clouds in case there's a wind blowing, and you see waterized clouds in this case. We also got albedo maps at 1.65 micron, and a lot of information about various cratering processes and collapse of the craters. This is a Pittal crater, which is one of the youngest and the largest collapse structures, which is seen in the area of Valles of Marineris. And this is somewhere around 2.6 billion year old. Menka experiment, looking at the Martian exosphere, we found for the first time how a carbon dioxide atmosphere converts to an oxygen-dominated atmosphere due to photoionization of CO2 and photodissociation. Essentially, O being lighter is dominant in the higher atmospheres. But this conversion takes place somewhere around 250 to 260 kilometers above the surface of the Mars in the evening time. And this was actually revealing because we are all thinking this transition is taking place around 220 to 230 kilometers. In addition, we also discovered superthermal argon on Mars. And this is important because in the exosphere, if you have any species which has little higher energies, it can easily escape. And therefore, this observation is now rewriting about how the Mars has actually lost its atmosphere because there are superthermal atoms which is present in exosphere, which is helping it to escape faster than it has been. We also use MOM in conjunction with MAVEN, that is a NASA mission, and Luckily, in this configuration, mom was in the evening side and Marvin was in the morning side. And this was a time frame when we had a planet encircling dust storm, PED event. And we found that the evening time Martian exosphere is much more swelled compared to the morning time. And this is also quite revealing information in terms of the dynamics which is playing in the Martian atmosphere. We also use MOM to look at the sun. When the Mars and the Earth are in the opposite side of the sun, it's called solar conjunction. And during this period, the signal passes through the sun's corona, and one can use that to do radio probing of the corona, which was done in the period of May to June 2015. And you can go down to almost like few solar radii to tens of solar radii. And this information has been converted into understanding of how the spectral index, which gives you indication of the acceleration of the solar wind close to the Mars corona of the sun. In the case of 2015, which was a subdued solar maxima, the activity starts saturating somewhere around 10 solar radii, whereas in the case of high solar activity, you see that continuing up to 20 solar radii. So that gives you indication about the activity changes in the sun's corona. And you must have all seen this, which is of course out of circulation now, that Government of India actually celebrated this Mangalyaan mission by putting the motif at the back of the 2,000 rupees note. Chandrayaan 2 mission is much more complex and complicated because we had a Vikram lander and the rover along with the orbiter. And we all know what happened during the landing on 7th of September. But the orbiter, which has 8 experiments on board, is working very well for the last 4.5 years, providing us excellently new data, and more particularly from this instrument called OHRC, which is having a resolution of almost like 1 feet at the moon surface. And this has been instrumental in deciding the landing site for the Chandrayaan 3 mission. We also had DAM generations using terrain mapping cameras. You can generate ortho images. And you may be happy to note that Dr. Sarabhai has a crater on the moon, which was very well imaged by the Chandrayaan 2 TMCs. And you can see it here, a big crater of 8 kilometer diameters and 1.7 kilometer deep. So if you have a small telescope, you can actually see this. We also look at a lot of signatures of boulder falls, which is called mass wasting. And this is one of the signatures where you see about 9-meter size boulder fall happening, which also suggests that there is a live activity happening on the lunar surface. And also looking at the global map of mare-filled craters on the moon, where we have used the data to understand how this volcanic activities would have filled this mare regions. And this is how you see the elevation changes happening as the material must have been filled into various of these spots, which is seen over here, which has been very well characterized now in the recent papers. The dual frequency radio science, dual frequency L and S band SAR and L and S has given us a lot of information beneath the surface, not above the surface, and up to a few meters beneath, because these frequencies can probe down. And if you look at this, you can see this is the fresh craters, this is the old craters, degraded craters, and they are all very clearly seen in this. If you compare this with the optical image, you can see that, yes, these are the actual locations where we are able to probe beneath the surface of the moon. The dual frequency radio science experiment doing occultation also has revealed a lot of information. One of them is that across the terminator, the densities are found to be quite large. It could be of order of 10 to 3 to 4 particles per cc. And the experiments like Chase giving us argon distribution, IARS giving us now a good map of water distribution on the lunar surface, the CLASS instrument providing us elemental composition and a map of the sodium, which is recently published, which talks about how the sodium distribution is there on the lunar surface. And for this to happen and convert this elemental composition into abundances, you need XSM. So there's an instrument called XSM, which is developed in PRL, which also is one of the most sophisticated instruments currently operating, providing us spectrum every 1 second in 1 to 15 energy band. And here you see how the solar activity changed from September of 2019 till January of 2024, very recently. And it has seen actually sub-A class microflare. Microflares of sub-A class has been seen, more than 100 of them have been seen, which is not possible otherwise because of the sensitivity of this instrument that you are able to see it. And it works in the energy ray, or basically the intensity scales of 5 orders of magnitude. So this is one of the best instrument which is able to provide you spectrum right from sub-A class to X class flares. Moving quickly to the Chandrayaan-3, we had this launch on 14th of July. This is integrated module where we have a propulsion module and a lander, that is the Vikram lander, and having a Pragyan rover inside it. So since we had the Chandrayaan-2 orbiter already moving around the moon in 100 kilometers, we only had a propulsion module to carry the lander to the moon. And this is all the integrated pictures of the propulsion module, the lander sitting on the top. And this is the launch pad a day before the launch. We had the fantastic launch on middle of the day on 14th of July. And after the launch, okay, let me just tell you about what is there on as an experiments. There is an instrument called SHAPE on the propulsion module. Other than that, there is no other experiment because our idea was actually use the propulsion module to go to the moon. There are 3 instruments on the lander. ILSA looking at the seismicity, Chaste going inside into the lunar surface to a 10 centimeter deep to provide the temperature profiles, and the Langmuir probe looking at the plasma distribution at the landing site at the height of the lander. And then we also have a NASA's lunar retroreflector arrays, 2 laser rangings. On the rover, we had 2 instruments, alpha particle access spectrometer and LIPS, and they are essentially meant to look at the elemental distributions at the lunar surface. So after the launch, we went into an orbit around Earth to gain velocities, and then we went into an orbit around the moon, and finally came down to 100 kilometer to 100 by 30 kilometer, and then we started descending down onto the lunar surface. Before the landing, all the sensors which is there on the spacecraft of Chandrayaan-3 were tested. One of them is lander hazard detection avoidance camera, which is shown over here. And there are many other sensors which are operated to see that all the sensors on the lander is working perfectly well. On the D-Day, I don't know where you were, but of course I was there in the mission control looking at the panels. And this is the day when we had the descent of the lander happening in the evening around 5:30 to 6 p.m. I will just show you a small movie and to reignite you of what all happened on 23rd evening.
The sensors that are updating at this point are providing confirmation of the safety of the landing site.
As expected, the retargeting is going on, and this is a very good signature for the lander.
So Prime Minister was there in South Africa that day, and he was watching it live from South Africa.
65 मीटर के आसपास
And we were all looking at various screens on the displays as well as the simulations, which is coming as a live feedback into the
Currently,
mission control.
only 2 engines are now being
In the
fired.
last phase, we have 2 engines which
And
are
we are
firing
nearly
just
at
till the launch
zero
touchdown.
velocity, vertical and horizontal. We were hovering, and now we are approaching the moon's surface.
धीरे-धीरे लैंडर की
And you can see this panel over here, which was coming as a live in the mission control. We were actually seeing how the lander imager is looking at the lunar surface, and
We
there
can
we
see
are.
the Honorable Prime Minister, Shri Narendra Modi ji, who is here to encourage us, and he is critically looking at
Now it is almost
the
vertical.
visuals.
It is coming down for the landing, and very soon you will see the engine shut off.
जी हाँ, आप अपने स्क्रीन पे देख सकते हैं कि हम लैंडर मॉड्यूल
People are applauding. Let us all wait to hear from the Secretary Department of Space and Chairman ISRO, Shri S. Somnath.
So this
लैंडर
is
मॉड्यूल पूरी तरह
the
से
landing, and everybody was over the moon. I was also over the moon, so I took this selfie immediately after the launch. But subsequent to that, when the whole country was under jubilation, we were busy in the mission control for the Pragyan rover, which is sitting inside the lander. And here you see the Pragyan rover sitting inside in the clean room. And this ramp has to be deployed to bring out the rover. So I'm going to show you a small clip now again. Can you play this? Okay. Or shall I do it? Okay, let me see. So this is how the ramp was deployed, and now the Pragyan is actually coming out. You see the wheels, the shadow, the Indian flag, and this is the place where it really touched down for the first time, the Pragyan. And this was the place when I was really trying to hold myself because there was a crater right in the front. And I was really worried that our baby, which has just landed onto lunar surface, should not go into the crater. So we had to make an assessment of that. We did that to find out the actual height of this using the navcam on the imager, on the lander, on the rover. And subsequent to that, we actually passed through this region. So you can see here the small crater was actually passed through by this rover. And this is how the 6-wheel rover is actually, and it started moving onto the lunar surface. We found a big crater in the front, and we said, oh boy, this cannot be passed through. So we rotated back. You can see the tracks of the rover. And this is actually the image which I really liked, which could be the image of the year or a decade, where you see how the Pragyan rover has taken the image of the Vikram lander. And you can see it near or far. And also, a lot of distribution around the landing site is very clearly seen, where people are working on this. The 3 experiments on the lander, the Chaste, seen over here very clearly, the ILSA sitting on the surface, and the Rambha, which was deployed, is very clearly seen as functioning very well. And how this rover was actually rotating in search of the perfect landing site. If you want to see how this boy was moving. See over here. This is, of course, a few hours of operation, condensed into half a minute of movie. And we are all trying to always see that the solar panels are aligned at 90 degrees so that you have the power generation. The APXS instrument, which was on the rover, was perfectly working well. And one of this captured movie will show you how the deployment system on the rover was working to take this measurements using the APXS or alpha particle acceleration. So there is a plate in the front which is moving, and the APXS get deployed and then make the measurements, and then it comes to the stored conditions. So you see the plate moving over here. So the rover is stationary during this time, and that is the time when we make the measurement both using APXS and the LIPS. So the rover moved around the landing site, which we now call as Shiv Shakti, and it moved almost like more than 100 meters around the landing site. And this is the path which it has traced. You can see we went into this, saw a big crater, went back, and then we came to know that this crater is fresh or new crater, and we wanted to go close, and that's why we went into this region to explore this area. The 5 experiments, the Rambha LP, the Chaste, the ILSA on the lander, and the APXS and the LIPS have performed very well. A lot of exciting science results have come out from that. Still, people are analyzing the data to understand, so I'm going to give you everything in one glimpses. This is how the temperature profile beneath the lunar surface looks like. We got signatures of even rover movement using the seismometer on the lander. So lander seismometer is gauging what is happening around when the rover was moving. We got excellent results from the Rambha LP about the charged particle distributions at a height of almost 2 meters above the lunar surface. LIPS and APXS has given information about the elemental compositions. People are looking at much more carefully into this and trying to simulate that conditions and do all the corrections. And the shape, which was actually on the propulsion module, which was moving around in the lunar orbit, also has provided us information about how the Earth will look like if you look Earth as an exoplanet. Hopping experiment was also done very soon after we complete all the science activities, and this was important for us to know whether we can actually do a lift-off from the lunar surface. And I will skip this. So this you see pre-hopping. You must have seen this picture. This is the ramp on which the rover came out. And after the hopping also, we moved almost like 2 feet away from the landing site. We lifted almost like 2 feet, moved about 2 feet, and came down. And after that, again, this deployment was done to test whether we can actually work after 10 to 12 days on the moon surface. The propulsion module, which was orbiting the moon, we thought we have enough fuel and can we do some experiment? And we thought we will bring it back around Earth orbit. So the propulsion module was brought back into a trajectory around the Earth, and now it is orbiting Earth. And this is also very important activity, which is technologically demonstrating that when we are going to do sample return missions, what is the kind of strategies we can actually adopt. What next? We are now working on a ISRO JAXA mission, which is basically going into the polar regions, particularly in the permanently shadowed regions, which don't see the sunlight. And our idea is actually to explore what is present over there. And here, the lander will be from India, rover will be from JAXA, Japan, but there will be experiments both on the lander and the rover, and the launcher will be from Japan, that is the JAXA H3 launchers. This is going to be about a 3 months mission where we'll be landing into a region which will be permanently sunlit in the polar regions, but the rover will go inside into permanent shadowed regions and then come back on the permanently sunlit regions to get charged and do this exercise. This is just a small road map of how the activity could actually take place and what are the places where we can actually go in this 3 months time frame, because the activity will be very slow. The rover movement also will be quite slow. But our idea is to look at the volatiles in the permanently shadowed regions, and this would be a precursor to ISRO's sample return missions. Subsequent to that, we are also talking about exploration of Venus and Mars. Venus is, of course, you know, is a very hostile planet with a surface temperature of 800 Kelvin, surface pressures of close to 100 bars. But if you go to the cloud tops, because the Venus is completely covered with sulfuric acid clouds, the pressures and temperatures there are quite benign. It is something like 1 bar and 300 kelvins. And therefore, a lot of speculations are there that probably life can actually sustain in Venus clouds. But of course, our idea is first to go and orbit around the Venus, to explore it in much more detail, using instruments for in situ and remote sensing. And for the Mars, since we have already gone to the Mars as an orbiter, our idea is actually to do a landing on the Mars. So these 2 missions are under discussion for real mission scenarios. In addition to this, we are also looking at how we can go further, Chandrayaan 4 or Chandrayaan 5 or Chandrayaan 6, both in terms of sample return missions and how we can have a future habitat on the moon. In the middle of that, we are also planning to have a Bharatiya Space Antariksh Station and the GL next generation launch vehicles, which is a heavier lift-off vehicle than the LVM-3 or LVM-3, where we can actually have a higher lift-off so that you can not only generate this space station, but also take humans to the moon. Once we go to human landing on the moon, we can actually start thinking about habitat on the moon or use moon as a base for doing future explorations. So that's why I put a lot of dots over here that how we can do this in coming decades for future. But all those youngsters who is present there in the audience, there is a lot of scope for you to become astronauts and actually do human landing on the moon. Thank you all for listening patiently.
A very exciting and enlightening talk. I'm sure there are a lot of questions, so we'll take a couple of quick questions.
What is the end date for this project of ISRO and Japan when it will tell something about the dark side of the moon. It is for 3 months. What is the date when it will come up for the first time?
You must have seen that this is under phase A. And so idea is not the dark side. It is permanently shadowed craters in the
Permanently
polar regions.
shadow side.
And the idea is that since those regions never see the sunlight, we can't explore them using solar fluorescence spectroscopy. So you have to physically go there and see what is present there. We all believe that all volatiles which is present on the moon in some point of the time in the geological time scale would have gone and must have settled there. And our idea is actually to explore that. Unless you go there, you cannot explore that. And that's why the idea is to go and see. Second thing is, how much water is there? How do we know that? Unless we really go and see it there.
Thank you.
Hello. So thank you so much for your talk. I had a two-part question. First is regarding the two maneuvers you told of the propulsion module, of the fueling module. First question is, can it be extended to, let's say, bigger payload missions? So if there are science missions that have been done on the moon, so do we have an upper limit on how much the propulsion module can be on the moon? And secondly, the two orbit maneuvers that you mentioned, which were taken and now it's in the orbit around the Earth, how are the decisions made for those? And is there any scope for doing science in those orbit maneuvers? Thank you.
So the propulsion module was actually designed because the lander weight was increased after the Chandrayaan 2 soft landing could not happen properly. And
solar output influencing atmospheric mass from Mars. But I'm just wondering, what is the possibility that CO2 and H2O might have diffused into the surface, and do we see the signatures of CO2 or H2O rich minerals on that Mars surface?
there's a lot of mineralogy
Any plans for the challenge of low pressure aeronautics?
Flyby for?
Flybys and sample returns were mentioned. Any plans for the challenge of low pressure aeronautics? Ingenuity. And other was the flow patterns which were shown. The top ones into the valley were sort of vertical, but there was something which was somewhat horizontal at the bottom. This is consistent with any topographic information.
Okay, so the first question was, I think, related to the Mars mission, where you're talking about what we'll do when we do the landing on the Martian surfaces.
No, low pressure aeronautics, ingenuity design.
Oh, what? Okay, oh, fine. Okay, yes. So this is a concept which is under discussion, more particularly for the Mars, because Mars has an atmosphere, right? And if you have an atmosphere only, you can have this kind of aerodynamical behavior of any instrument where you can fly, like Ingenuity. So that is one thing which is being discussed about, whether it will be similar to Ingenuity or something else, whether you can have a hover or a rover or a copter. Yes, that is being discussed, particularly for the Mars mission, because after landing, not only you can rove around, but you can also do hovering, and you can cover a larger area compared to that at the landing site. And the second question is with respect to flow pattern. That is for the moon you must be talking about, right?
No, the Mars channel.
Oh, channels, right. So this is a regular feature which has been seen on
Okay. Good afternoon, everyone. Let me first of all thank ASI for giving us an opportunity to put in front of you the capability of Aditya L1, which is currently now at Sun-Earth Lagrangian point. And we have also started switching on the instruments, and currently it's in the performance verification phase to ensure all the planned activities as well as the planned observations can be carried out with this particular mission. I'll just briefly touch upon what the capabilities of Aditya L1, and I'll also show you some of the sneak peek of what we have or what we could do so far with this particular satellite. I'm not going to the launch and other details, straight away going to the science aspects of it. And as you can see, this is our heliosphere, and this is governed by the solar events, solar particles, as well as the energetic events coming from the sun. And what you have seen is the coronal mass ejections and the solar flares, which is originated from the sun. And the gray lines, what is depicted is the interplanetary magnetic field, which is the Parker spiral coming from the solar magnetic field. And as you know that the particles tag along with the Parker spiral to reach to the Earth. And Aditya sits somewhere here, closer to the Earth than to the Sun, and which can watch both the Sun as well as the particle which is streaming towards the Earth. So the idea behind this particular mission is to study what is happening on the Sun using remote sensing payloads. We have 4 remote sensing payloads which looks at the Sun continuously, and which will provide the information about the dynamical events which happens on the Sun. Of course, when I say dynamical events, it consists of all kinds of spatial as well as the temporal scales, what we could see on the Sun. And we also have in situ payloads, which looks at the particles which is thrown into the interplanetary medium and which is reaching to the L1. It's called in situ because it samples the regions in situ to the satellites. So any particles and magnetic field which is in the presence of satellite will be measured by these in situ particles. And this will give us information about those particles which is crossing this L1, and most of the particles, especially if they are connected to the Earth through the magnetic field lines, will come and land up on the Earth. So it also provides us an indications to the early warnings of some of these high energy events which is coming towards the Earth. The primary science goals, though this is put as a kind of a science goals based on the instruments. I will also cover some aspects of it. I think we should look at Aditya as an observatory class rather than an individual instruments. I will also put up few science cases which can be done with this kind of observatory class missions. So the major science goals, what we see here is the plasma dynamics for the large as well as the small scale structures in the corona. And of course, one of the major thrust for this particular mission is to look at the close to the Sun CME dynamics, which is hardly we have any major data which is available for us to study the initiation mechanisms of these coronal mass ejections. And this would also provide the first space-based coronal magnetic field measurements, which will provide us both the magnetic topology of the corona as well as the field strengths, especially over the active regions, and which also provides us with the spectroscopic capabilities, provides us the ability to do these abundant studies, especially with respect to the FIP variations during solar flares, and prominence studies. And again, this is the first missions where we will do a spatially resolved irradiance variations in the 200 to 400 nanometer band to identify the variability associated with the solar source regions. That would be carried out from this particular mission. And of course, since we do have in situ measurements looking at different directions, and hence it will provide us both the directional and energy anisotropy of these solar events which comes from the Sun. It also provides us an indication to talk about the events, which is whether it is due to the SEP events, solar energetic particle events, or these events are due to the CME shock-related events, by looking at the size scales of these events using the in situ measurements. Here is an example of observatory class missions, what Aditya can do by looking at the Sun as well as the interplanetary connections. What I have put together is a small cartoon of events which happens on the Sun. What you see on the left-hand side is a nice little bipolar loops. When it gets disturbed due to more bipolar combinations coming from the Sun, or due to more of flux emergence which is happening on the Sun, there can be rearrangements of this magnetic field. What we call it is a reconnection physics. And the reconnection physics is actually seen as solar flares in the solar atmosphere. And these flares are captured by these X-ray instruments. And as the reconnection happens, the particle starts to flow in both the directions. It's a kind of a bidirectional flow. The particles flows back into the solar surface, and the particles also are thrown into the interplanetary medium. The mass fluxes which is thrown into the interplanetary medium is seen as coronal mass ejections, which is seen by the VELC. So a good combination of X-ray time variation of these events and the CME propagations in the coronagraph images will provide us the link between these, especially the flare-driven CMEs. And once the CMEs propagates into the interplanetary medium, and it would reach to the L1 points, and where we can sample them for different properties of these particles in terms of its distributions, as well as in terms of its velocity, temperatures, and other parameters. And the electromagnetic radiations, the flare also provides the particle which is going back into the sun. These are all highly energetic particles which are accelerated by the reconnections. And these accelerated particles do provide information in the hard X-ray band of the electromagnetic radiations. And as the particle comes back and hits the chromosphere, the chromospheric heating starts to happen, and that shows up as a ultraviolet enhancement in the radiation. So soot and X-rays, especially hard X-rays, can play a major role in identifying the populations which are going back into the solar atmosphere. And the coupling of the inner and outer corona is seen by the regions. The soot images covers the full disk images, and as well as a larger region in the corona, whereas the VELC covers from 1.05 to 3 solar radii. So there is a good overlap of tracking the events from the disk to all the way up to the 3 solar radii. So that also can be done with this particular instruments. Okay. So this gives you a gamut of studies which we can do. Of course, I have also put few wavelength band which India has the capability to look at it. One is the radio band. We do have solar observations in the radio band. Radio band also captures these accelerated particles as well as the coronal mass ejection. So one could combine effectively the ground-based observations to maximize the signs coming out from Aditya L1. Of course, there is also a ground magnetic network facilities which tells us about the geomagnetic indices and geomagnetic events which happens due to the solar events. This is one case for looking at the Sun-Earth connections as well as the using the Aditya capability to the full potential. Here is few examples. I mean, of course, people have tried to do it. I mean, that's human mankind tried to do with whatever limitations what we have, tried to do the best out of it. Here is one case study of with the existing instruments, looking at the UV images as well as the chronographic images from the ground-based observations. You can see that you do get the high time plot. And from the high time plot, you can actually calculate the velocity, accelerations, and what more. And we do see a lot of correlations between these multiple events taken at multiple wavelength band. And this gives you a good indications that Aditya can cover a large portion of these events when we start operating as an observatory class mode. Here is an example of recent observations from the data from the ACE and WIND missions, which is also at L1 point. These are some new observations which needs validation and verifications, and of course Aditya will play a major role in doing this. What you see here is distributions of the change in the field directions coming from the in situ magnetic field measurements. And here what you see here is the data points from the alpha to photon, alpha to proton ratio. They do have a certain distributions. And this distribution is related to the kind of events which you are capturing at that particular moment. And they do have there's certain structural integrity in the magnetic field. For example, here if you see the lower part of the change in the field directions corresponds to the flux variations within the magnetic tubes, and the upper part is tells you about the tube walls. And this sudden change in the magnetic boundaries also has an indication that this change is reflecting on the solar source surface. I mean, so the magnetic flux tube which is coming from the sun during these events are retained, has not been disturbed, is what these results are indicating to us. This is only one or two results which has been come out from ACE and wind. Aditya will be able to take this up to the further levels. We also have this both particles, electromagnetic radiations from multiple waveband, and with NUV suit instruments on board Aditya L1, we will have this light curve populated with NUV light curve, which we don't have currently as such. And what we see with the existing NUV measurements from the limited observations we have, we do see that the NUV light curve has a mixture of soft X-rays as well as the hard X-rays, which means that the NUV band picks up the accelerator particles, which is related to the hard X-rays, and also the cooling part of the flaring regions, which is after the peak of the soft X-ray light curve. So NUV samples both the regions, so it gives you much more information than what currently we have. So these are the certain cases where we can do with multiple payload capabilities of Aditya L1 and use it as a kind of an observatory class mission. I'll just go into certain details of the instruments, and before I come to the initial results, Aditya is conceived with 7 payloads, 4 of them of remote sensing and 3 of them in situ payloads, and these pictures depict where they stand. The biggest one, which is sitting on the top deck, is the VELC, and next one, which is the next biggest one, is the suit instrument. I think there is a problem with the color here again. It's supposed to be green. And this is an aspects instrument, which is the in situ particle instruments. And this is the high energy X-ray instrument, which is sitting inside the top deck of the satellites. And the PAPA and the magnetometer, which is in the stored conditions on the boom, is sitting in the panel which is facing the sun, and the Solex is hiding below the suit instruments. So these are the 7 instruments which constitutes the Aditya satellite. Of course, when I say 7 instruments, it's not 7 sensors. It has many more sensors. So as an instrument, it's only 7. The number of sensors are many more than the 7 numbers. So I'll just go through few observations what we have obtained and tell you the kind of capabilities what we can utilize in the next many years. So this is a suit instruments which works in the near ultraviolet band with filter-based imaging capabilities. It has 11 filter combinations, so that means you can take 11 different images at different filter combinations. The filters are chosen such a way that you sample the atmospheres at different heights. So, so you would be able to study the properties of different atmosphere at least near simultaneously using these 11 filter combinations. So these are the filter combinations. You see these 8 are narrowbands, all the way starting from 1 angstrom filters to up to 50 angstrom filters to cover different portions of the solar atmosphere. Especially we cover 2 interesting and important lines in the chromosphere, calcium and magnesium lines. And we do have a 3 continuum band, which is mostly used for the irradiance variations studies. And they are in the band such a way that these bands are related to some of these NUV bands which is used to study the Earth's atmospheric dynamics. So we could actually provide input to the Earth's modelers with the solar radiations, solar irradiance coming in these particular bands. Suit entrance door opened on December 5, 2023, if I can run this movie. One good thing about this particular mission is we do have two cameras, which is not a science cameras, but a camera to look at some of these operations which is put on board. And probably you would have seen the one camera which has looked at the Earth during the Earth-bound orbit. This is a camera which is put on board to look at the multi-operating door mechanism operations of suit and VLC. So what you see here is the opening mechanisms of the suit, and there is one more door sitting there is for the VLC that is yet to be opened. And since it has a multi-operation door capability, it opens and closes based on the ground commands from here. This is needed because both the suit and VLC instruments are very sensitive for contamination. So during any of our maneuvering for keeping the orbit intact, when we use these thrusters, these doors will be closed to keep the performance of these instruments intact. So this is one of the images from the magnesium 4 angstrom band images. What you see here is different features, the sunspots, plages, as well as the quiet sun. Of course, there is a small defocus in the images when I see it from here and there. The resolution is better than what you see here on this particular screen. So the chromospheric filters are sensitive to these magnetic fields on the sun, and what you see here, all these plages and the sunspots, is an indication of the magnetic activities of the sun. Here is an example of a zoo of images, 6 of them which I had put together. Again, there is a issue with the Again, there is an issue with the projector. This is not empty here. There are images there in that region. So what you see here is the magnesium band in the line core, in K and H band, and in the wings of the magnesium. And this is the filters at 300 nanometer to bring the high contrast features of the sunspot. And this is the broadband images in the 320 to 360 nanometer. Of course, these images are not corrected for any flat fielding or any other corrections are not be done. These are all raw images. There's a lot of work need to be done to bring it up to a science ready portion of this. Here is an example of suit capturing the first solar flare in this particular region, and it's an interesting event. This is captured by many other payloads on Aditya L1, including the X-ray payload as well as the in situ payloads. It will be interesting to look at the science from these particular observations, though it is a performance verification phase observations. We do see some interesting science which we can carry out with this. Move on to that. This is the X-ray instrument, SOLAX, low energy X-ray spectrometer, covering 1 to 22 keV. It also had an entrance aperture to protect the detectors from the Van Allen belts during the launch phase, during the initial phase of earthbound operations. And that aperture door was opened on the 13th of December, and I think we have been very lucky enough that as soon as we opened the door, the sun became very active. So on that particular day itself, we started to see many flares on the 14th and 15th day. So you can see one X-class flare, this is X2.9, and 2 M-class flares and many C-class flares, which we could see. And what you are seeing here is the light curve from SOLAX and matched with the light curves of the GOES. And so we are yet to convert this counts per second into this flux unit. Needs certain calibration parameters which we need to apply before it can come into it. The difference between GOES and SOLEX is SOLEX can do spectroscopic capability, which GOES does only two-band observations. So we also looked at the spectroscopic capability of SOLEX. Again, it's not look good. Maybe that is better. That is also not good. Okay, so what I wanted to show you here is a spectra with few features. What you see here is these iron line features and an iron nickel complex, and there are calcium and silicon and sulfur lines which are seen. And this plot shows the light curve converted into counts per second into watt per meter square, and compared it with the GOES as well as the SOLEX light curve. So we have a pretty good handle on the light curve informations, and also we could able to fit the spectra and derive the parameters like the temperatures and the abundances variations for this particular flare. This is a C6.5 flares happened during December 30th. Going to Helios, which is a high energy part of this X-ray payload, which covers, actually it was designed for 10 to 20 keV, 10 to 200 keV. Currently we can, our low energy threshold can go down to 8 keV. So right now we are operating from 8 keV onwards, the instrument. And it also has a reasonably good resolutions. You can see 0.8 keV at 14 keV. And here is an example of the flares which is observed during the initial phase operations of the Helios. And of course, we have compared with the GOES, and the energy bands are different. The one shuttling difference, what you see here is Helios, since it's a high energy part of it, will peak before the GOES light curve peaks. Given both SOLEX and Helios, we can combine the data together to study a few interesting aspects of it. Here is an example of a very interesting pre-flare activity which is captured by both, all payloads, Helios, SOLEX, as well as the GOES instruments. What you see here is different light curves. The Helios light curve is 1 to 22, is shown in this blue curve. And Helios from 6 to 30 is shown in this green curve, and 30 to 150 keV is shown in this green curve. So what I want you to notice here, these small sporadic events which is happening just before the main flare happens. These are all related to some of these small scale reconnections which happens before the main reconnections start to happen. We do have spectra for this, shows very interesting phenomenon. We are in the process of fitting them together, both SOLEX as well as Helios together as a single spectra, and derive the properties of them. Going on to it, and this is a particle instruments which carries multiple sensors to look at different directions, to cover the both ecliptic plane as well as the out of ecliptic plane, and this gives you the energy range of the particles which this can see. One unique feature of this aspects payload is it can also differentiate between hydrogen and helium, and the alpha to proton ratio what I showed you, these instruments can provide a very nice data to it. Here is an example for that. What you see here is the hydrogen and proton as the event passed by. So this is the event of an X 2.8 flares which I showed you in the SOLEX light curve. That particular event also had a CME which propagated in the interplanetary medium, and aspects started to see these CME disturbances in the day of December 15th, the next day. Aspects has two payloads. One looks at the ecliptic plane, another is looking at the perpendicular to the ecliptic plane. You do see similar signatures for those events in the perpendicular to the ecliptic plane too. This is from the STEPS instruments. So the Swiss instruments looks at the proton events which is coming from them, as well as the hydrogen and helium separations. This STEPS instruments looks at the high energy protons part of the events. And again, you can start to see that the events started to capture at different sensors mounted at different orientations on the satellite. So you have a sensor oriented along the Parker spirals. You have sensors oriented at different locations away from the Parker spiral. So we do start to see these events crossing by from CMEs. Here is an example of some events which happened, taken both from Swiss instrument as well as the wind instrument. You can see that they correlate very well, and we do have a very seamless variations from different energy band compared to the wind instruments, because wind limits their energy band depending on where the peak comes from. So they don't detect the energies where there is no peak in there. So that's why you see a lot of empty spaces here where we will be able to capture the advantage over the wind. PAPA is very similar to aspects, but looks at the electrons. And this was also switched on sometime in December. And you can see the electron events, again, which happened on the 15th of December. Again, similar to the flare and CME, which happened on December 14th. There's a good correlation with the magnetic field for these electrons, and that is what we expect. Unfortunately, we don't have the magnetometer turned on that particular day, so I don't have the data from Aditya for this particular event. MAG, which was switched on October 16th, in the stowed conditions, started to see some events. This is an event which happened in close to November 5th or so. What you are seeing is the magnetic field in BX obtained from Discover spacecraft in L1 and the Aditya. Aditya is shown in the red, and you do see a very good correlation. Of course, you also see the differences. The differences are due to some of the operations which we carry out at the satellite, because it's in the stowed condition, any activity which is happening on the satellite also affects the measurements, magnetic field measurements. We could actually identify what activity happened at this particular durations on the satellite. This is BY and this is BZ. VELC, which is one of the stringent instrument to switch on, because we cannot switch on without going into the without putting the sun into the occulter positions. Was switched on with the door closed, and luckily they had a ND filter in the front door, so we could see the sunlight through the ND filter. Here is an example of the sunlight, sun disk, what you see in the continuum channel, and we know that VLC has 4 slits. So the 4 slit positions also gives you the spectral informations from the spectroscopic channel. Here is a spectra taken one cut, and you can see that the disk lines, you can see it here, and the coronal line, which will fall at 5303 angstrom, definitely falls in the center of the band, which is what is designed for. So spectroscopy is ensured, and we will get a good spectroscopic data from here. We are on the process of putting this the sun into the occulter mode. So you can see this dark region, which is the occulter region. You see the very slim portion of the sun there, like an eclipse. We'll be pushing them into the occulter before we open the door for it to see the coronal light. I'll skip this. I'll just want to say a few words about the support cell, which is formed by ISRO. The idea behind this is to make use of this particular data and reach out to the larger community of the country. And Dipankar has taken a lead on this particular support cell. He has organized many meetings, many sessions with many of your young people. And I would urge you to be in touch with him, because this is the time where we will start to train with the actual data soon, so that you will be able to start utilizing this particular data for your future science observations. With that, I will stop, and thank you once again for the good opportunity you have given.
Any questions for this talk? I'm sure most of you are feeling hungry and would want to rush for lunch now.
Time resolution of the spectra from the VLC spectra. Okay, so the time cadence of the spectra can be anywhere from 150 milliseconds to several seconds. So we have a capability to operate the detector as fast as the exposure time can be as low as 1 milliseconds or below. Even hundreds of microseconds is feasible, because it's a CMOS sensor. But the readout time is the one which limits the lowest time cadence, which is roughly about 150 millisecond. And you can also define what kind of cadence you want. So when you put up a proposal, there is a column where you can choose what is the exposure time you need and what is the cadence which would be required. Depending on the science, you can modify that particular portion.
Hello, thank you very much for the talk. I have a question regarding magnetometer. So I think I didn't understand that very well. What kind of observation we are expecting with magnetometer?
Okay, so the magnetometer, the in situ magnetometer, what we have, it will measure the local magnetic field as any of the events passes by, as well as the interplanetary magnetic field, which is already existing, because you have this path.